Right, hell yeah. So I'm going to go over kind of one of my study processing techniques or whatever. So hell yeah. So I wanted to look up basically what proofs were, you know what I mean? And basically proofs are, and what question did I write in? Is it reasonable to be confused about what a mathematical proof is because one proof might be used in the finding of another proof? You know? And I said it seems like we would have to prove that integer numbers are evenly spaced. And then I started studying. And one place that kind of what we're going to talk about was, I looked up what is deductive reasoning. So, and then, heck yeah. And then the hierarchy of proofs. It says the process often involves proving smaller lemmas, which are then used as an intermediate step to prove larger, more significant theories. And then so I said, what is a smaller lemma in math that is used to prove something higher? Hell yeah. Okay, so, and then I misread this actually. It says in the proof that the square root of 2 is irrational. So that's where I just thought they were talking about a lemma, because it says a lemma is like a subroutine in a program. It's a smaller piece of code that helps you to build the bigger programming. So sweet. So, but I read this wrong. I read in the proof of the square root. I read the proof. Well, let's just read this. In the proof that the square root of 2 is irrational. So there's a proof to show that. One of the lemmas might be used to show that if you have a square number, and so we're going to go over this because a might be a number, and if you had a squared, that's a squared number. Maybe a squared is now like b, so b is the number. B is a square number because it can be represented as a squared. If I take the square root of a squared, then we get a. So then it says, then its square root must also be even. So if I start with an even number a, and then square it, is going to be even. And then, so then if I take the square root of that, so, and lemma might be used to show that if a square number is even, then the square root must also be even. Cool. And then so this lemma is used to ultimately prove the larger statement about the irrationality of the square root of 2. Cool. So I wrote in, what is this theorem called? If a square number is even, then its square root must also be even. And it just said that's what it's called. If the square of an integer is even, then the integer itself is even. Cool. So I asked why in this theorem the definition of an even number has to be an integer. Cool. And then it said in a theorem about even numbers, the definition must use integers because the concept of evenness is intrinsically tied to whole numbers. And then that kind of just blew my mind because for whatever reason, I'm thinking an even number is just a positive number. And it took me a while to get there. And I was just like, why am I confusing positive number with even number? And it took me a while to even come up with that statement. So hell yeah. And so we have, let's see what we got. It says many examples of positive numbers are also even numbers. But it says when you first learn about numbers, you are likely to encounter positive integers like 2, 4, 6, 8, which are both positive and even. And so we come down here, hell yeah, negative even numbers. You know what I mean? And so I never really liked formal definitions, but when it comes to math, holy Toledo, you might be thinking one thing where, you know what I mean, the person or the author or the textbook is saying something completely different. And so definitions for math are absolutely critical. And so just kind of using AI is a pretty good example of like, hey, just ask a question because I might be thinking one thing. I didn't really realize you had negative even numbers, or what the hell an even number actually was. And then that's why we're getting into the proofs, because it says, hey, even numbers are integers divisible by 2 with the remainder of 0. So you could have integers that are, and I get how integers are negative or positive whole numbers. But let's say we take -3 and we divide by 2. Using long division, it's going to divide once, but then we're going to have a remainder. We're going to have a remainder of, 3 divided by 2 is 1.5, or -1.5. And so that's -1 with a remainder of a half. So hell yeah. So -3 can be divided by 2, but you're going to have a remainder of 1/2. And so hell yeah, or -1/2 if you what I mean, however that works out. So hell yeah, so that's going to be the formal definition of what an even number is. All right, hell yeah. So let's see where we go from here. Why doesn't the square root of 2 violate this theorem that says if a square number is even, then its square root must also be even? Because I guess, well, and now I'm just reading it, is 2 a square number? Well, 2 is not a square number, but we're going to go over how they prove this. And so then we wrote, how can this theorem, if a square number is even, then its square root must also be even, be used to prove the irrationality of the square root of 2? Let's see what else. What is a coprime? Because, yeah, that definition is going to come up. What's coprime? So let's look at this. A coprime is where you have two numbers, and if those two numbers' greatest common divisor is 1, then they're coprime. And so, you doing the prime factors of 15, we get 1, 3, 5, 15, and 8 goes 2, 2, 2. And so both, 1, 2, 2, 2. So their only common factor is 1. Cool. So is this a lemma? If a square number is even, then its square root must also be even. No, this statement is if a square number is even, then its square root must also be even is not a lemma. It is a proven statement, and it's a theorem used as a stepping stone to prove another more significant. Oh, so it says a lemma is a proven statement used as a stepping stone to prove another more significant theorem. This statement, while true, is more of a definition or a basic property of even or square numbers. So I didn't even get that right. But anyway, and AI and Google AI is going to have some variance. But hell yeah. So let's go over. I think I can do this. I just read it, but so what we are trying to do, maybe get this a little bit bigger. Now we're going to go back to this. What you're solving for. You are proving the irrationality of square root 2 using the theorem that if a square number is even, then its square root is also even. And so that's where I'm just looking at this 2 as a square number, maybe. I don't know. So I just look at number 2 and it looks like it's even. So why doesn't that, I must just be confusing something. So let's kind of dive in. And so so what's given in the problem? If a square number is even, then its square root must also be even. Cool. And we know that the square root of 2 is not even, so the 2 must not be a square number. No, if a square number, 2 must not be a square number. So let's see if that's what they're going to do. 2 must have to be represented as, let's see what they do. So helpful information. Proof by contradiction assumes the opposite of what you want to prove. A rational number can be written as a divided by b, where a and b are coprime integers. Okay, hell yeah. So this is, and I guess they would be coprime integers because it's the most reduced way to write a over b. So a rational number can be expressed in its most reduced way because a and b are coprime integers. You could say this is 1 divided by 2, but you could also say this, and it would be nonsensical to say 2 divided by 4 because that could be reduced to 1 divided by 2. 2 divided by 4 is not coprimes because 2 and 4 both have 1 and 2. That's going to be 2. And 4 is going to be 1, 2, and 2. And so they're not coprimes. They also share other primes. They share 2 as a prime. Coprime meaning they only share one common divisor, and that's 1. Okay, hell yeah. So how to solve? Assume square root 2 is rational. That's what they're going to do. So we're going to say 2 has to equal... oh, no, they're actually just saying the square root of 2 is rational. Okay, and that's how they're going to prove this. Prove by contradiction. So we're going to assume that square root of 2 is a over b. I've never done this one, so it's just kind of fascinating to see where I, so I kind of even, I had one assumption that the 2 was going to be a divided by b. That's not, you know what I mean? So it's good also to be on your toes, to be able to quickly discard things that you mentally thought, but then are not what they're going for. So we're going to assume the square root of 2 can be in this rational form a over b, where a and b are co-prime integers. And then the whole proof, because I read it all the way through, if we can prove that a and b, through this process are not co-prime integers, like where a and b are both a factor of 2 or have to be a factor of 2, then then we've contradicted ourselves. And so the only way square root 2 is rational if a over b are co-prime integers. All right, hell yeah. Hopefully that makes sense to me. Cool, so step 2 says square both sides. Cool, so now we're going to square this. I'm going to get 2 and then a squared and b squared. I can see that. And then you're going to get b squared up there. So we got 2b squared is equal to a squared. And now we're going to use, apply the given theorem to a squared. It says since a squared is equal to 2b squared, a squared is an even number. Now, is that going to be true? Yes, because one of the theorems is that if you have, and hopefully they go into that, but if this was 2b squared plus 1, then this would be an odd number. But no, we just get 2b squared. So probably this might be, anyway, I'm trying to figure out what would be, lemmas and what would be actual theorems. It's kind of fascinating. So by the theorem, and this is a theorem, it's not even a lemma, but by the theorem that if a squared is even, then a must also be even. Cool. And then there's something here that, just by the way this looks, and probably another proof or theorem, that this says that a squared has to be even. Well, so if b is so it doesn't even matter. B can be an odd number. Cool. Let's say it's 7, and we square it to get 49, which is also odd. But we're going to take that odd number and multiply by 2. So as long as this is an integer number that we're multiplying by 2, then this a squared has to be even. And then so, by the theorem that a squared is even, a must also be even. And since a is even, we can write a as 2 times k for some integer. Because any even number, let's say it's 2, can be written as 2 times 1. 4 can be written as 2 times 2. So there you go. Cool. So now let's see what they do next. Hell yeah. So now we're going to substitute this value for a into that equation. And that equation involved, b squared, 2b squared is equal to a squared. So I think that's where they're going to go next. So we have 2b squared is equal to a squared, which is 2b squared is equal to 2k all squared. So it's going to be 4k squared is what you're going to get. And now we can get b squared is equal to 2k squared. And I kind of now get what they're going. If a and b are both even numbers, then a can't be 1 and a can't be 0. You know what I mean? So a would have to be 2. And if b is an even number, it can't be 0, it can't be 1. It also has to be 2 or some even number. And then so if you have a multiple of 2 top and bottom, then that's not coprime. So a rational number can be written as a over b, where a and b are coprime integers. And so if this number was 2 divided by 2 is 1, I don't know, so it's kind of fascinating. So let's see where they go. That's as far as I got. so far. Okay, so so now we're going to apply that apply the theorem to b squared. B squared is equal to 2k squared. It's not 2k squared plus 1. And so we can use that same idea, is that if k is an integer, any integer squared, doesn't matter if it's 3 squared is 9, but then if you multiply it by 2, you're going to get an even number. So b squared is an even number. So by the theorem b squared is even, then b must also be even. So we have found that both a and b are even. This means that a and b share a common factor of 2. This contradicts our initial assumption that a and b are coprime. The assumption that the square root of 2 is rational leads to a contradiction. Therefore, square root of 2 must be irrational. And honestly, the aha moment does not just, like, the fireworks aren't going off right now at all. But I guess this is where I'm kind of stumped, is like, okay, we're going to say square root of 2 is rational. We're going to assume that. And it can be written as a divided by b, where a and b are coprime integers. So that's where I'm kind of stumped. You know what I mean? Because it seems like we just proved that a over b could be even. But I guess that's not a rational number. Can be written as a over b, where a over b are coprime integers. And then so if we, so I guess, and then here's where I can pick up a little bit. You know what I mean? If, because, and I get this because I've been trying to do as many proofs as I can in linear algebra. And one of the things that I've done is this process of proof by contradiction, is try it. Like this to me now rings bells, and I didn't even realize that. This is the try it method. If you think this is equal to something, try it. And guess what? In the end, these are not going to be equal. You know what I mean? So that's what we can do here. We can say, well, if you think the square root of 2 is equal to a over b, and that's where this proof is interesting to me. I guess I just don't get this idea that a and b have to be coprime integers. It seems like they could just be anything. But I guess if, I don't know, I think we were close on the fact that if a and b are in their lowest kind of form, their most reduced form, a and b will be coprime integers. Because if they're not coprime integers, and this is a function, this is a factor of 2, and this is a factor of 2, then you could reduce it to be such. And then so that is where the juice of this this proof comes in. But again, it's a little bit stretchy for my mind the first go, where it's just like the aha moment's not just so evident that we're saying that yes, these are coprime, but I'm a little bit closer. Like, hey, we are saying that these are coprime. We're not saying that they're not. We're not saying that they could be coprime or not be coprime. No, we are saying that they're coprime. And then when we run through and we square this side and then bring this b squared upstairs, we actually get what the value of a should be. And the value of a has to be, or the value of a squared, let's say, has to be even. And if the value of a squared is even, then a has to be even. And if a is even, it's a factor of 2. You know what I mean? Because that's one of the definitions of even numbers. And then we can do that same thing. We can solve for b squared. Once we know a squared is going to be as some sort of 2k, 2 integers. So I can talk my way through this one a little bit better. Then we're going to get b squared up there, and we're going to have a squared divided by, or this 2k squared divided by 2, which is going to be 2k. And because this is in a form, they should do like another proof here instead of just saying this, but we did our own. We said that if k is an integer, we could even choose an odd integer. We could choose a -3. -3 times -3 still is 9, still negative. Multiplied by 2 is positive. And therefore b squared is positive. If b squared is positive, then b must be even. And, sometimes I just use the proof of like, try it. 2 squared is 4. 4 squared is 16. Try to pick any even number that's squared, and that's going to contradict. You know what I mean? But that's still not good enough. Because my brother says, he's like, well, maybe at the far reaches of the number system, that doesn't apply. So You know what I mean? So just proof by overloaded examples is not, it's a good start though. You know, just throw some examples in and see if you can see a pattern. But hell yeah. So I don't know I've never looked up this formal proof of, but I see it, you know, if I have an integer, this proof. I don't know the formal proof that if a number is squared, then the number itself, since b squared is 2k squared, b squared is, this one. By the theorem, I need to look this one up once I'm done making this video, that if b squared is even, then b must also be even. Cool. Okay, I need to look that one up. But therefore, a and b are both even. And so we found that a and b are both even, which contradicts what we set up. So that was the most important thing. Because when we set up this equality, we're saying this equal sign, that a and b have to be coprime. You know what I mean? They have to be, but still, that's like still a little bit wishy-washy to me. But I'm slowly understanding what was happening there. Hell yeah. If you can explain why the aha moment goes off for you, that for sure we set this equal to a and b being coprime. And when we, so still walking through that process, solve for a. Like, what is a? Well, a is even and b is even. And we just solve for b and b is even. So these actually aren't coprime. Still, like, I get that a little bit, but still, like, the aha moment's not super solid on that for me. It's not just glaringly like, whoa, that proof for sure proves that square root of 2 is irrational. But hell yeah. But that is it. The assumption that square root of 2 is rational, like equating square root of 2 to be rational, leads to that contradiction. Therefore, square root 2 must be irrational. And this was fascinating. I mean, give a like if you've made it to the end, I guess. I mean, hell yeah. Because obviously I'm making these videos from the standpoint of like, hey, I didn't know something, and now I know something. I know a little bit closer towards something. And even just making this video, if the aha moment just bursted for you, hell yeah, go for it. You know what I mean? But for me, it's just a little bit. We're getting there. Slow is fast. Hell yeah. And we looked up what coprime is. And if this is a lemma, so I said if this is a lemma, if a squared number is even, then its square root must also be even. And it says, no, this is not a lemma. A lemma is a proven statement used as a stepping stone to prove another, more significant theorem. This statement, while true, is more of a definition or basic property. See, I don't even know what the hell they're even talking about in this one. So, you know what I mean? But we actually looked it up. We figured out maybe what a lemma is, what a theorem is, what a proof is. A little bit. So hell yeah, thanks for joining me, and that's a video.